Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo. I'm studying chemical physics and math. Today I'm going to be going through some high school level and college level calculus problems. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. So for our first question, we're looking for the derivative of secant x. And for this one, we're going to be using the quotient rule. So let's just write that down first. And so we need to remember that secant x is equal to 1 over cos x. So this tells us that the derivative of secant x will be equal to the derivative of 1 over cos x. And then we can go about finding this using the quotient rule. And so if we set f of x is equal to 1, that means that the derivative is equal to 0. And g of x is equal to cos x, which means that the derivative is equal to negative sine x. So we're just going to put that all into our formula so that we can get the derivative of 1 over cos x is going to be equal to 0 by cos x minus 1 by negative sine x all over cos squared x. These two negatives will cancel and this is 0, and that will leave us with sine x over cos squared x. We can separate this out into sine x over cos x by 1 over cos x, and we know that these identities are tan of x and secant of x. So this tells us finally that the derivative of secant x is going to be equal to tan x by secant x, and that's your final answer. Next up, we'd like to find the parametric and symmetric equation of a line passing through the point 2, 3, 4, and that is perpendicular to the plane 5x plus 6y minus 7z is equal to 20. So there are many ways that we can get the equation of a line. And so we are given the first option is you could have a point and a normal vector. You could have two linearly independent vectors. And lastly, you could have 3 points that are nonlinear. And so from these 3 points, you could technically derive 2 linearly independent vectors, and from those 2 linearly independent vectors, you could derive a point and its normal. So for our problem, let's start by finding our normal vector, because we want it to be perpendicular to a specific plane. And so for the plane 5x plus 6y minus 7z is equal to 20, its normal vector is just going to be these coefficients. And so it's going to be 5, 6, negative 7 is going to be our normal vector. And so since now we have a point in our normal vector, we can just write that x, y, z is equal to the point that we have. So 2, 3, 4 plus this normal vector multiplied by a coefficient. so a constant. So 5, 6, -7, and we can call that constant t if we'd like. And then for our parametric equations, we're going to write down x is equal to a specific thing. So constant plus a multiple of t, y is equal to the same thing, and z is equal to the same thing. So let's start by doing that. So x will be the x component plus this x component multiplied by that constant. So 2 plus 5t. Y is going to be 3 plus 6t, and z is going to be 4 minus 7t. Okay, and then next up for our symmetric equations, we are going to simply solve for t in all of them. So you can get some function of x is equal to some function of y, which is equal to some function of z, and these are all going to be equal to t. And so in our first case of x is equal to 2 plus 5t, solve for the t so that we can get x minus 2 is equal to 5t, divide both sides by 5. And so our function of x, which is going to be equal to t2, is equal to x minus 2 over 5. So let's write that one out first. Okay, and then now we do the same thing for the parametric equation involving y. And so with y is equal to 3 plus 6t, we're going to move that right on over to get y minus 3 is equal to 6t, and then we're just going to solve for t. So our function of y, which is equal to t, will be y minus 3 over 6. And then lastly, let's look for a function of z using the parametric equation involving z. So with z is equal to 4 minus 7t, we can actually bring the 7t over and bring the z back. So we get 7t is equal to 4 minus z over 7 to get t is equal to our function of z, and that's going to be 4 minus z over 7. So 4 minus z over 7. And so for our final answer, we have our parametric equation and our symmetric equation, and those are your final answers. Next up, we would like to evaluate the statement. So we want the limit as x approaches infinity of arctan of e to the x. And so in order to find this, we need to think about what happens to our function here as x approaches infinity. Whatever that thing is, we can simply evaluate arctan of basically e to the infinity is what we're looking for. And so we know that if we look at the limit as x approaches infinity of e to the x, that is going to give us infinity. And if you simply look at the graph of e to the x, you'll be able to see that. Let's go ahead and pull that up. Okay, and so we can see that as x is going to infinity this way, our y value is also going to infinity. And so what that means is that the value of the limit of e to the x as x approaches infinity is infinity. And so now we are basically looking for the arctan of infinity. And we know that tan of pi over 2 is an interesting spot on the graph of tan, because at pi over 2 it goes to infinity. And so what that means is that tan of pi over 2 is equal to infinity. And then if we just convert this into the inverse trig form, it becomes arctan of infinity is equal to pi over 2. And we can really have any multiple of pi over 2, as you can tell by this graph. And so we could write it as n pi over 2. And so what that means is that the limit as x approaches infinity of arctan of e to the x is equal to arctan of infinity. And that is going to give you, let's leave it as pi over 2. You can write 3 pi over 2, 5 pi over 2, any multiple of pi over 2 that is not even numbered. And so our final answer will become the limit as x approaches infinity of arctan of e to the x is pi over 2, 3 pi over 2, and that's it for this question. Okay, next up we are going to look for the derivative of b to the x. And so how we're going to do this is we need to note, let's say y is equal to b to the x, right? Let's take the logarithm of both sides. It can be to any base. So let's just use base 10. And then we're going to use the property that d over dx of log u is going to be 1 over u multiplied by d over dx of u. Additionally, we'll use the fact that log base a of b to the, let's use c as our variable, would be c log a of b. And so we're going to use this to write out both sides of the equation. This is going to become our left-hand side, and this is going to become our right-hand side. And so we know that log y is going to be 1 over y, first we're going to take the derivative of both sides after rewriting this. And so we know log y is equal to x log b. Take the derivative on both sides. Rewrite everything. So this becomes 1 over y. D over dx of y is equal to d over dx of x log b. And then next up, you're going to use the property that the derivative of some function by f of x is going to give us the same thing as a constant multiplied by f of x is going to give us the same thing as that constant multiplied by the derivative of f of x. And so we're going to apply that here so that we can get 1 over y d over dx of y is equal to, our constant is log b, because log base 10 of a constant will give us a constant. So log b d over dx of x. Now let's just write out y in terms of what we initially had. So we know y is equal to b to the power of x. And so we know that 1 over b to the power of x multiplied by d over dx of b to the power of x is equal to log b d over dx of x. We know that this is going to give us 1, and we know that this is what we're looking for. And so if we just solve for the derivative of b to the x, we will get log b multiplied by 1 multiplied by b to the power of x. And so that means that our final answer is going to be equal to b to the power of x multiplied by log b. And that's it for this question. And so, sorry, let's use, as I said, you can use any base. This question use base e. And so that becomes b to the power of x of ln b. Okay, next up we want to figure out how to convert between polar and rectangular coordinates. Let's just write down what that means. Rectangular is Cartesian, so you're using x, y, z coordinates. And with polar, instead you're using some radial coordinate and some angular coordinate. And so polar would typically be best in like scenarios where you're looking or you're dealing with circles that have a certain radius. And so now let's write out what each of these coordinate systems are. With the rectangular system, if I have a point here, I would identify it using its x coordinate, so how far on the x-axis I have to travel. So if I have whatever point, I travel on the x-axis and I travel on the y-axis to reach my point. Apologies. To reach my point, oh god, up here. And so if I identify the point in red, I would say that that point is located at whatever distance it traveled on the y-axis and whatever distance it traveled on the y-axis. So I'd identify it with x, y, if we're working in 2D. Now with my polar coordinates, instead of doing that, and identifying it with those two pieces of information, instead, if I have my point located at this point in space, I will travel along the line directly to it, so the shortest distance to it, and we'll call that r, and I'll just take a note of what angle I'm making with the x-axis, so theta. And so those are the two coordinates that you're using. And so if I want to be able to find, basically convert between polar and rectangular coordinates, so if I wanted to find r from this, I can see quite clearly that r is going to be just here. And so using our right angle Pythagoras theorem, I know that r will be equal to x squared plus y squared. And that theta I can find by doing the inverse tan of y over x. And that's simply on SOHCAHTOA. So tan of this angle is opposite over adjacent, y over x. And then I simply solve for theta using inverse trig. Okay, so this is how I'd get polar coordinates from rectangular coordinates. Now I need to figure out how I can get rectangular coordinates from polar coordinates. And so again, just apply Pythagoras and draw out your right angle triangle. And from this, I can see that x, y, if I use SOHCAHTOA, that means that sine of theta would be opposite over the hypotenuse, so that would be y over r. And that cos of theta would be adjacent over the hypotenuse, and so that's going to be x over r. And so if I wanted to solve for x and y here, and I only have polar coordinates here and here, so also in the equation, then I can be able to do so. So y is going to be r sine theta, and x is going to be r cos theta. And so this is how you convert from polar coordinates to rectangular coordinates, and this is rectangular coordinates to polar coordinates. And that's it for this question. Next up, I would like to find the general solution of the differential equation given, find a singular solution that is not included in the general solution, and inspect a sketch of typical solution curves to determine AB, for which the initial value problems y prime is equal to y squared has a unique solution. And so first, if we have dy over dx is equal to y squared, let's actually bring all of our y terms to one side and all of our x terms to the other side. So this becomes dy over y squared is equal to dx. And then next up, you simply, my apologies. Yeah, you simply integrate both sides. And so I'm looking for the integral of 1 over y squared dy is equal to the integral of dx. We know that this is the same thing as y to the negative 2 dy is equal to the integral of dx. And we know that the integral of y to the power of a is going to be 1 over a plus 1, y to the power of a plus 1. And so with negative 2 as your a, that becomes 1 over negative 2 plus 1, y to the power of negative 2 plus 1 is equal to, I'm not going to put the c term on this side. Instead, I'm going to put the c term with the x because I want to get my final answer in the form y is equal to some function of x plus c. And so this x plus c. And then let's just write out what this becomes. This becomes negative 1 y to the negative 1 is equal to x plus c. And so if we rewrite that, we can get y is equal to negative 1 over x plus c. So you just bring the y to this side and the x and plus c to the other side. And so this is going to be your general solution to the differential. So that's part A. Next up, we want to find a singular solution that is not included in the general solution. We will see here that, so we have y prime is equal to y squared. If we put in our values, we'll get that the solution at the point x is equal to 0 is not included in the solution. And that can be easily seen if we just, so x is equal to 0 isn't included because the denominator being 0 can't be evaluated, but the equation would still technically hold. And so it's not included in the equation that we've found as the general solution to the differential equation, but it is a solution. And so our answer for that part will be x is equal to 0. You can evaluate it to just ensure that the solution is true and that does hold for our DE, but obviously it's not going to be included here. Next up, we want to expect a sketch of the typical solution curves. And so here we have our curves. And so for which initial value problem does it have a unique solution? And so you're just going to examine through this curve to determine at what point does it have just one solution, and that's it. Next up, we're looking for the derivative of secant x tan x. So we're going to be using the product rule, and that just states that the derivative of ux times another function of x is going to be equal to okay, so you take the derivative of 1 multiplied by the other function plus the derivative of the other function multiplied by the other one. And so if we're looking for, if we have our u of x is equal to secant x and our b of x is equal to tan x, we can go about finding their derivatives. So d over dx of 1 over cos x, using the quotient rule, we'll find it's 0 by cos x minus 1 by negative sine x, all over cos squared x, and we found this to be equal to secant x tan x. And so if we're integrating this, you get the answer of secant x, but that's not what we're looking for today. Next up, we look for d over dx of sine x over cos x. And so that is going to become cos x by cos x minus negative sine x by sine x all over cos squared x. And so this just becomes 1 over cos squared x, and that is secant squared x. And so that means that u prime x, which is our secant x, is equal to secant x tan x, and b prime x is going to be equal to secant squared x. And so now we're just going to put that all into our formula here. So our u, the derivative of ux, so secant x tan x, multiplied by bx, which is tan x, plus the derivative of bx, so secant squared x, multiplied by ux, so secant x. And then if we just simplify that, that becomes secant x tan squared x plus secant cubed x. And then we can pull out one of those secant x's into tan squared x plus secant squared x. And that's it for this one. Next up, we want to evaluate this integral. And we're going to be using integration by parts. I know it's tempting to use the acronym here, where we have inverse, trig, inverse trig, algebraic, trig, exponential, logarithmic. And so we choose u according to this. But we're actually not going to do that. We're actually going to set our u of x equal to x and our dv equal to secant squared x dx. The reason that we're doing this is because it's easier to integrate secant squared x than it would be if we chose x secant x. And so that's just why we're doing that, because you typically want a dv that is easy to integrate and a u of x that is easy to differentiate. The acronym is just a quick way to remember which ones would be optimal to choose, but it isn't always true. And so now if we go about finding the derivatives, we find that du is equal to 1 dx, so dx. And we know that the integral of secant squared x is going to give us tan x, I believe. Yeah, tan x. And so now we're just going to put all of that into our formula. Let's just write out that formula. Integral of u dv is equal to uv minus the integral of v du. So with what we have here, we get that the integral of x secant squared x dx will be equal to x tan x minus the integral of tan x dx. And so now we need to evaluate this. So let's just rewrite it in its other form. We know that tan x is equal to sine x over cos x. And then we're going to use substitution here. And so as you know, if we happen to get it in the form of the derivative of f of x over f of x integrated over dx, we can simply set u is equal to f of x. That way, when you look for du over dx, which will be f prime of x, you'll get that dx is equal to du over f prime x. So when you substitute everything back in, the f prime x's will cancel, and you'll just be looking for the integral of 1 over u du, which we know. And so that means that since we know the derivative of cos x is equal to sine x, we can do that here. And so we set u as sine x, which means that u as cos x, which means that du over dx is negative sine x. And this means that dx is equal to du over negative sine x. Substitute that all back in here. So we get the integral of sine x over u, and then substitute dx to become du over negative sine x. These two will cancel, leaving a negative. So we just pull it out to become the negative integral of 1 over u du. The negative is coming from that part. And so the integral of tan x dx is equal to the negative integral of 1 over u du. This is going to be negative ln the magnitude of u. Then just put back in u. So negative ln the magnitude of cos x. And so now we're going to put that all back into our formula here. Negative over negative is positive. So this is just some of the rough work so you could understand where it's coming from. And so this will become x tan x minus ln of cos of x. And then now, since we've gotten rid of all of the integrals, we can put the plus c now, since it's an unbounded integral. So we get x tan x plus ln of cos of x plus c is equal to the integral of x secant squared x dx. And that's your final answer. Okay, so for this one, we're going to find the second derivative of y by implicit differentiation when x squared y plus xy squared is equal to 3x. And so for this one, we just need to note that d over dx of u times v is equal to d over dx of u multiplied by v plus d over dx of v multiplied by u. And so we want d over dx of this entire statement. So 3x is equal to x squared y plus xy squared. And so that's going to be d over dx of dx is equal to d over dx of x squared y plus xy squared. Additionally, you will use the fact that d over dx of f of x plus g of x is equal to d over dx of f of x plus d over dx of g of x. And so we're just going to apply that to separate this out. So let's call this 1. We'll use 1 to separate it out, and then we're going to use 2 to figure out these products. And so d over dx of 3x is simply 3 is equal to d over dx of x squared y plus d over dx of xy squared. And then we start to use the product rule. And so first take the derivative of x squared. So that becomes 2x multiplied by y plus x squared multiplied by d over dx of y, we can just write y prime, plus d over dx of x, which is 1 multiplied by y squared, plus d over dx of y squared. We know that the power rule will leave you with 2y multiplied by y prime. And so that becomes 2y, y prime. Multiplied by x, because we were dealing with the second term here. So let's just write that properly. And this is all going to be equal to 3. So using this, now we solve for y prime for the first derivative, and we'll get that y prime is equal to 3 minus 2xy minus y squared all over x squared plus 2xy. So we found our first derivative. Now we want to find the second derivative, so d over dx of y prime, and we are going to be using the quotient rule. So let's just write that out. Can put these in brackets so that it's a little bit clearer. All over g of x squared. So what this means is that d over dx of 3 minus 2xy minus y squared over x squared plus 2xy. Let me just write that a little smaller so it can all fit. This is our g of x. And then we're going to do minus, my apologies, this is supposed to be a minus, d over dx of x squared plus 2xy multiplied by our numerator. So 3 minus 2xy minus y squared. All of this is going to be over our denominator squared. So over x squared y squared. And so now let's go about finding all of these. And so if f of x is equal to 3 minus 2xy minus y squared, f prime of x is going to be equal to, this term will drop off. And then we're going to use our product rule. So the derivative of this with respect to x is negative 2 multiplied by y. Sorry, let's leave the negative out, actually. So it becomes negative. So 2 multiplied by y plus, we have 2x y prime minus, this becomes 2y y prime. Now with g of x is equal to x squared plus 2xy, our derivative will become 2x plus, and then again we're going to apply what we know about the product rule. So this will become 2y plus 2xy prime. And so now we're just going to put that all back into our formula up here. And from this, we get the second derivative is equal to 2x to the power of 4y sorry, let me just write out everything so it's clear. So negative 2y y prime minus 2y minus 2xy prime into x plus 2y minus 3 minus y squared minus 2xy into 2x plus 2y plus 2xy prime. And this is all going to be over x squared plus 2xy squared. And then now let's multiply these out. And we will get 2x to the power 4y plus 3x cubed y squared. Let's actually write this out smaller again. So we get 2x to the power 4y plus 3x cubed y squared plus 3x squared y cubed plus xy to the power of 4 plus x cubed y plus 3x squared y squared plus 3xy to the power of 4 plus 2y to the power of 4 minus 3x cubed plus 3x squared y minus 9xy, sorry, minus 3x squared minus 9xy minus 6y squared minus 9x. And then you can zoom out. So it's quite a long answer and a long process to find this answer. But this is all going to be over when you expand out that denominator, x cubed over x plus 2y cubed. Okay, and so now let's simplify that. And so we will get as our final answer, we will get 2x to the power 4y plus 2x to the power of 4y plus 3x cubed y squared plus 3x squared y cubed plus 4x y to the power of 4 plus x cubed y plus 3x squared y squared plus 2y to the power of 4 minus 3x cubed plus 3x squared y minus 3x squared minus 9xy minus 6y squared minus 9x. And this is all going to be over x cubed into x plus 2y cubed. And this is going to be your final answer for the second derivative. And so it's a bit long and messy, but if you just write out all of these parts on the side and ensure that you get to the right part here, and then multiply correctly and collect the like terms, you should get the correct answer. Okay, next up we want to be integrating cosecant squared x. Okay, and so this is actually a standard integral. I know that the answer should be negative cotangent x plus c. It's just the standard answer. It should be integrals that you're actually quite quick with. But assuming that we don't know that, it would be tempting to choose to try and use substitution and write out the fact that this is equal to the integral of 1 over sine squared x dx. And then next up, we would want to say that u is equal to sine squared x, and then find the derivative and continue like that. But what you'll get is that the derivative of sine squared x is going to give you another term with an x term. And so when you say dx is equal to du over what's left, it's going to give you a function of x. And so when you try and insert it here, you'll be left with u terms and an extra x term, and we can't integrate that. And so this is not the correct method to continue down. Instead, I'm going to make a slightly informed substitution and instead choose u is equal to cotangent x. And so that would be cos x over sine x. That means that du would be equal to negative sine x into, du over dx is equal to negative sine x into sine x minus cos x into cos x all over sine squared x. And this becomes negative sine squared x plus cos squared x all over sine squared x. And so we get negative 1, because this is equal to 1 according to the identity that we know, over sine squared x, and this would be negative cosecant squared x is equal to du over dx, and that means that du is equal to negative cosecant squared x dx. And so we can just write that. And you'll notice that the reason why I made this substitution was intentional. So let's just write out negative cosecant squared x dx. So that means that dx is equal to du over negative cosecant squared x. Yep, and so clearly here we can see that we are getting it into a form of f prime x du over f prime x, and so these two will cancel. And so now if we use the substitution that we have here, we have the integral of cosecant squared x du over negative cosecant squared x. And so because u wasn't appearing anywhere here, I just proceeded by substituting in our dx. And so these two will obviously cancel, and we get negative the integral of du. This will give you negative u, and then just put back in what u actually is. So this becomes negative cotangent x, and then because the integral is unbounded, that becomes negative cotangent x plus c. This is why it's just known as a standard integral, because we made a basically informed guess. Okay, next up, we are looking for the derivative of y is equal to e to the power of 2x. There's two ways that we could do this. Let's use first off substitution and the chain rule. And so that just states dy over dx is equal to dy over du multiplied by du over dx. And so if we did it this way and we had u is equal to e to the 2x, is equal to 2x, then we'd have d over dx of e to the u is equal to dy over du. Let's just write it out on the side. Dy over du is going to give you e to the u. So let's write e to the u multiplied by, if u is equal to 2x, du over dx is going to give us 2. So multiplied by 2. And then now we're just going to substitute back in u is equal to 2x. So it becomes d over dx of e to the 2x is equal to e to the 2x by 2. And that's going to be your final answer. Alternatively, if again you start with y is equal to e to the power of 2x, let's first begin by taking ln of both sides. Okay, and then we note the fact that ln e to the 2x would be equal to, and this is just based off of logarithm properties, so log base e of e to the 2x is equal to ln e to the 2x is something that we need to note. Additionally, we need to note that log base a of a is equal to 1, and log base a of b to the power of c is equal to c multiplied by log base a of b. And so first, we can rewrite this as log e to the power of 2x. That's going to become 2x multiplied by log e, and then that's just going to become 2x, because this will cancel out to become 1 according to this rule. Okay, and so let's stick with this is all equal to ln y. Next up, we're going to want to take the derivative of both sides. Okay, and then we know that if we have d over dx of ln u is going to give us 1 over u multiplied by d over dx of u. And so let's write that out. So it becomes 1 over y, d over dx of y is equal to d over dx of 2x is just going to give us 2, just using the exponent rule. So when a is equal to 1, it becomes 1 over 1 multiplied by x to the power of 0, so just 1 over 1. And so 2 by 1 over 1 is 2. And so now we substitute back in the fact that y is equal to e to the power of 2x, and this becomes 1 over e to the power of 2x multiplied by the derivative of e to the power of 2x is equal to 2. And then we solve for what I am looking for, and it becomes d over dx of e to the power of 2x is equal to 2 multiplied by e to the 2x. And that's the exact same answer that we had reached using the other method. And so those are your final answers. Next up, we're looking for the integral of 2x. I'm going to be using the fact that the integral of a constant multiplied by some function of x dx is equal to that constant multiplied by the integral of f of x dx. And then additionally, I'll be using the exponent rule, so that states that the integral of x to the power of a over dx is equal to 1 over a plus 1 x to the power of a plus 1. I just reversed the exponent rule that we know as the derivative of x to the power of a is equal to 1 over ax minus 1. Sorry, x to the power of a minus 1. So that just means that the derivative of x to the power of a plus 1 is going to give us 1 over a plus 1 x to the power of a. So that's why we have this. Okay, and then I'm going to use that to simplify this problem a little bit. So the problem becomes the integral of 2x dx is equal to 2 multiplied by the integral of x dx, and that is going to be equal to 2x squared over 2. These two will cancel, leaving x squared as the integral of 2x dx. And then I'm just going to add the plus c. If you want to ensure that this answer is correct, just take the derivative here. And so it will become 2x leaving the 1 and then the c would cancel because you're taking the derivative and it's a constant. And so this is going to be your final answer. And those are all of the questions that I have for you today. I hope you enjoyed today's Q&A session. If you'd like to be notified of when OneClass posts more videos like this, be sure to hit the subscribe button and the bell next to it. If you'd like to be able to post questions of your own so that they can be answered over a Q&A session, be sure to check out the links in the description. This has been Marlyn from OneClass, and I hope to see you next time.